Have you ever pondered over the nature of space and time? This question has baffled many minds, from ancient philosophers to modern physicists. The enigma of space and time is a cornerstone in our understanding of the universe. It's an intricate tapestry woven by the threads of relativity, a theory that has revolutionized our perception of the cosmos. Introduced by Albert Einstein in the early 20th century, the theory of relativity shattered the conventional ideas of space and time. It painted a picture where space isn't a static stage and time isn't a relentless march. Instead, they intertwine in a cosmic dance, bending and stretching under the weight of matter and energy. This theory, as complex as it may seem, has profound implications that are far-reaching. It's not just about black holes or the expanding universe, but about the very nature of reality itself. Now, let's dive deeper into one of the fascinating consequences of the theory of relativity: length contraction. Can something in motion appear shorter? According to the theory of relativity, it can. Let's dive into the concept of length contraction, an intriguing phenomenon that challenges our everyday understanding of space and time. At the heart of this phenomenon lies Albert Einstein's theory of relativity. It tells us that the universe doesn't quite work the way we perceive it in our daily lives. Among the many startling revelations of this theory, one is the idea that the length of an object in motion can appear to contract or shrink when viewed from a stationary frame of reference. Now you might be wondering, is this some kind of optical illusion? Surprisingly, it's not. This is a genuine physical effect. The object isn't actually getting smaller, it only seems that way to an observer in a stationary frame of reference. Here's where it gets interesting. This contraction isn't noticeable for objects moving at everyday speeds. It only becomes significant when an object is moving at a speed that is a considerable fraction of the speed of light. To give you an idea, light travels at a speed of approximately 300,000 kilometers per second. So, we're talking about speeds that are so high they're almost unimaginable. At these speeds, the laws of physics as we know them start to bend in ways that are counterintuitive. And that's what length contraction is all about. It's a testament to the fascinating and at times mind-boggling realities of our universe, revealed through the lens of relativity. The physics of the very fast is not just about numbers and equations. It's about redefining our understanding of the universe and our place in it. It's about embracing the fact that reality can be stranger and more complex than our everyday experiences might suggest. But how can we visualize this concept? Let's take a ride on a spaceship. Imagine a spaceship zooming past us at nearly the speed of light. It's quite a sight, isn't it? Now, if we were to measure the length of this spaceship from our stationary position, we'd find something astonishing. The spaceship appears shorter in the direction of its motion. This phenomenon, known as length contraction, is one of the most intriguing consequences of Einstein's theory of relativity. You see, space and time are interwoven into a four-dimensional space-time fabric. When an object moves at speeds close to the speed of light, this fabric alters its shape, leading to length contraction and time dilation. Let's focus on our spaceship. To us, the stationary observers, it seems as if the spaceship is squeezed in its direction of motion. It's like the universe is playing a cosmic game of push and squeeze, making the spaceship appear shorter than it actually is. But if you were on the spaceship, you wouldn't notice any change in its length at all. Why? Because you'd be moving with the spaceship, you're in the same frame of reference. The length contraction is only observable from a frame of reference that's stationary with respect to the spaceship. This is the relative nature of observation Einstein was talking about. Now, let's touch upon time dilation. Remember the spaceship's clock we mentioned? To us, the observers, it would appear to tick slower. Yes, slower. Time, like space, is affected by the speed of the spaceship. The faster it moves, the slower its time seems to pass from our perspective. But again, if you were on the spaceship, you wouldn't notice any change in the clock's ticking. It's all relative. So, we see that the length contraction is a fascinating consequence of the theory of relativity. But what does it imply? Length contraction might seem like a purely theoretical concept, but it has profound implications. Delving into the implications of length contraction, we must first acknowledge its influence on our understanding of space and time. When we talk about space, we're usually thinking about something static, something unchanging. But length contraction introduces a dynamism to space. It suggests that space is not a fixed entity, but can actually change based on the relative motion of observers. This is a significant departure from our everyday perception of reality. And it's all thanks to Albert Einstein's theory of relativity. Now let's consider time. Length contraction implies that time is not universal, but relative. If you're moving at a significant fraction of the speed of light, time will appear to slow down for you compared to someone who is stationary. This is known as time dilation, which is closely related to length contraction. Together, these two phenomena give rise to the concept of spacetime, a four-dimensional fabric that weaves together the universe. But it's not all theoretical. Length contraction also has practical applications. For instance, it plays a crucial role in the functioning of particle accelerators. These machines accelerate particles to speeds close to the speed of light. At these speeds, the particles experience significant length contraction, which allows them to travel further in the accelerator before decaying. Similarly, global positioning systems, or GPS, also take into account length contraction. The satellites used in GPS are moving at high speeds relative to the Earth and hence experience time dilation and length contraction. To ensure accurate positioning, the GPS system needs to correct for these relativistic effects. Despite these implications and applications, it's important to note that length contraction has yet to be directly observed. This is because it requires speeds close to the speed of light, which are currently beyond our reach. However, the indirect evidence supporting length contraction is robust and compelling. So, what are the key takeaways from our discussion on length contraction? Length contraction, a concept born out of the theory of relativity, challenges our everyday perception of space and time. It's a remarkable idea that takes us into the realm of high-speed physics and forces us to rethink the way we understand the universe. To recap, we've delved into the enigma of space and time, unraveled the concept of length contraction, and used the analogy of a fast-moving spaceship to illustrate this theory. We've seen how an object in motion, such as our spaceship, appears shorter in the direction of its movement when observed from a stationary frame. This isn't an optical illusion or a trick of the light, but a real physical effect resulting from the relative motion between observer and observed. In the context of our spaceship, from the perspective of a stationary observer on Earth, the spaceship appears contracted, shorter than its actual length. Meanwhile, from the perspective of someone inside the spaceship, everything would seem normal, with no apparent contraction. This shows that length, just like time, is not absolute, but relative to the observer's state of motion. We've also touched on the implications of length contraction. It's not just confined to the realm of theoretical physics or the vastness of the cosmos. It plays a role in the operation of particle accelerators, where particles reach speeds close to the speed of light, and their contracted length is a key factor in their behavior. Length contraction, like many concepts in the realm of relativity, might seem abstract, even counterintuitive. But it's these very concepts that challenge our perceptions, push the boundaries of our understanding, and open doors to new scientific and technological advancements. So, as we conclude our journey into length contraction, let's take a moment to marvel at the fascinating world of physics, a world where the ordinary becomes extraordinary and the impossible becomes possible. So, next time you look at a fast-moving object, remember, in the realm of high speeds, things aren't always as they seem.